Here is the part most explanations of black holes skip. It is not the crushing gravity. It is not the darkness. It is not even the fact that nothing can escape. It is this. If you fell into a black hole, you would not feel anything unusual. At the moment, you cross the point of no return. No alarm, no sensation, no indication whatsoever that you had just crossed a boundary from which the entire rest of the universe is now permanently unreachable. You would only know it was too late, because eventually the tidal forces would take you apart. But by then, of course, it would not matter. Here is what a black hole actually is. Actually Science, Episode 6, Black Holes from Scratch. The misconception. Black holes are not what you think. The most common mental image of a black hole is wrong in an important way. People picture them as cosmic vacuum cleaners, giant mouths in space, actively pulling everything nearby into destruction. This is not how they work. A black hole does not pull on objects any differently than any other mass of the same size would. If the Sun were somehow replaced by a black hole of identical mass, Earth's orbit would not change. We would lose our light and heat and die very quickly, but we would not be sucked in. The gravity would be exactly the same. The reason black holes seem so extreme is not because their gravity behaves differently from other gravity. It is because their mass is compressed into an almost unimaginably small space. That compression is what changes everything. To understand why, we need to start at the beginning. Not with Einstein, not with Hawking, with a dying star. The ground floor, how a black hole is actually made. A star is a balancing act. On one side, gravity, pulling all the star's mass inward toward its center. On the other side, the outward pressure of nuclear fusion, which converts hydrogen into helium and releases an enormous amount of energy in the process. For most of a star's life, these two forces are in equilibrium. Our Sun has maintained this balance for approximately 4.5 billion years. It will maintain it for roughly another 5 billion. But eventually, the hydrogen runs out. The fusion process slows, the outward pressure drops, gravity wins. What happens next depends on the mass of the star. For stars like our Sun, the collapse produces a white dwarf, a dense, cooling remnant roughly the size of Earth. For more massive stars, the collapse is more violent. The core compresses so rapidly that it triggers a shock wave that blows the outer layers of the star apart in an explosion called a supernova. What remains at the center after a supernova depends on how much mass was involved. For the most massive stars, those more than around 20 to 25 times the mass of our Sun, nothing can stop the collapse. The core keeps compressing past neutron star density, past any known state of matter, until it reaches a point of infinite density called a singularity. A black hole has been born. The singularity is surrounded by what we call the event horizon. The event horizon is not a physical surface. There is nothing there you could touch or see. It is a mathematical boundary. The point at which the escape velocity required to leave the black hole's gravitational pull exceeds the speed of light. Since nothing can travel faster than light, nothing that crosses the event horizon can ever return. Not matter, not radiation, not information of any kind. The size of the event horizon, called the Schwarzschild radius, depends entirely on the mass of the black hole. If you compressed the entire Earth down to its Schwarzschild radius, it would be approximately 9 millimeters across, a marble. For our Sun, the Schwarzschild radius is about 3 kilometers. For the supermassive black hole, at the center of our galaxy, Sagittarius A star, which contains approximately 4 million solar masses, the event horizon is about the size of the orbit of Mercury. In 2019, the Event Horizon Telescope collaboration published the first direct image of a black hole's event horizon. The supermassive black hole at the center of the galaxy M87, 55 million light-years away. The image matched the predictions of general relativity with striking precision. Why it matters: time, radiation, and the paradox that broke physics. General relativity predicts something deeply strange about time near a black hole. The stronger the gravitational field, the slower time passes. This is not a metaphor. It is a measurable, physical fact. GPS satellites have to correct for it every day. Near a black hole, this effect becomes extreme. From the perspective of an observer watching from a safe distance, an object falling toward a black hole appears to slow down as it approaches the event horizon, getting dimmer and redder as its light is gravitationally stretched until it seems to freeze at the horizon and fade from view. From the perspective of the object itself, or the person falling, nothing unusual happens at the horizon. They cross it in finite time, feeling nothing. They simply cannot communicate this fact to anyone outside. This is the first deep strangeness of black holes. Two observers watching the same event experience it in completely irreconcilable ways. Both are correct. General relativity does not resolve this. It produces it. In 1974, Stephen Hawking published a paper that seemed to contradict everything we thought we knew about black holes. By combining quantum mechanics with general relativity, Hawking showed that black holes should not be perfectly black after all. They should emit a faint thermal radiation, now called Hawking radiation. The mechanism is complex, but the essential idea involves quantum effects at the event horizon. In quantum mechanics, empty space is not truly empty. It is filled with pairs of virtual particles constantly flickering into and out of existence. Near the event horizon, one particle of a pair can fall in, while the other escapes. The escaping particle carries energy away from the black hole. Over astronomically long timescales, this causes the black hole to slowly lose mass and eventually evaporate. Hawking radiation has not been directly observed. For stellar mass black holes, it is so faint it is currently undetectable with any instrument we have. But the theoretical prediction is widely accepted, and it created the most troubling unsolved problem in theoretical physics. The frontier, the problem nobody has solved. Here is the information paradox. In quantum mechanics, information is conserved. This is a fundamental law. The complete quantum state of a system at any moment contains all the information needed to reconstruct the system's entire past and future. Information can be scrambled, transformed, made practically inaccessible, but it cannot be destroyed. Now consider what happens when something falls into a black hole. A book, a star, a person, whatever it is, it carries quantum information. It crosses the event horizon. It is gone. If Hawking radiation causes the black hole to eventually evaporate completely, where does that information go? Hawking's original calculation suggested the radiation was perfectly thermal, random, carrying no information about what had fallen in, which would mean the information was destroyed. This would violate one of the most fundamental laws of quantum mechanics. Hawking himself spent decades arguing the information was truly lost. Most physicists disagreed. In 2004, Hawking conceded the point. He accepted that information probably escapes, somehow encoded in subtle correlations in the Hawking radiation. but he admitted he did not know how. Neither does anyone else. The information paradox remains unsolved. Some of the most brilliant physicists alive today are working on it right now. We do not yet have the answer. Actually Science. Complex science, actually explained. Follow us on YouTube at Actually Science though.